In today's video, let me tell you about a special kind of white noise called binary white noise, why it's special and how to make it. But first of all, I'm going to play 4 white noises. See if you can hear a difference. Despite sounding the same, they're all different. We have Gaussian white noise, triangular white noise, uniform white noise, and binary white noise. Each of these at exactly -12 RMS. And because white noise has a flat spectrum, a flat frequency response, loudness, which we measure using LUFS, is therefore also -12 for each of these white noises. So we have 4 different noises, same loudness, same spectrum, and they sound the same. However, the waveforms peak at very different levels. Same loudness, sound the same, but peaking at different levels. To keep things simple, let's focus just on Gaussian and binary. These other ones in the middle are simply in the middle, so let's focus just on the extremes, Gaussian and binary. So at the same loudness, Gaussian peaks at -3, whereas binary peaks at -15, 12 dB lower, and remember, these sound basically the same. And the lower it peaks at a fixed loudness, the more headroom we have when producing. So let me zoom in to show you what's happening. First of all, on Gaussian. Here we have Gaussian white noise. See those tiny dots? Those almost white or maybe grey tiny squares? Those dots along the line are the samples, the digital samples. Ignore the line connecting them for now, we'll come back to that. Notice how the dots, the digital samples, are at a range of heights. Whereas in the binary white noise, the dots, the digital samples, are at a fixed height above or below the middle. This is why it's called binary white noise, because the samples are at one of only 2 different values. This is the magic of binary white noise, and knowing where the samples are helps us create it. To make binary white noise, we need to wave shape some normal noise. Most DAWs have a wave shaper, but there is a free plugin to do this from Melda Production called M Wave Shaper. And as you can see, this is free. We'll set dry wet to 100 so we get just the wave shaped sound, and then we want to map all points to maximum. So I've inserted a node and dragging it exactly to the top left corner. Bing! Render! See how all the dots are exactly along the top and bottom now, which we can verify if we normalize to the same RMS as before. And since binary peaked at -15, -15 should do the trick. See how all the dots, the digital samples, are at one of 2 values now, just like in binary noise. So checking waveform stats and comparing to the original binary white noise, RMS on our wave-shaped one is also -12, and peak level is also at -15. So we have indeed created binary white noise. Saying all that, there is an easier way, and this is what I did to create the original binary white noise. Use a binary white noise generator in Isotope RX. Either way works. One way is easy, one way is free. Now, I need to point out something important. So let's go back to the original Gaussian white noise and compare to binary white noise. Notice how for binary white noise, true peak level is over 7 dB higher than digital peak level, listed as sample peak level here in RX. So the intersample peaks, the true peak overshoots, are over 7 dB higher than digital peak. If we're zoomed out, we're looking at digital peak level, but if we zoom in, the blue line you see connecting the samples is the true peak level. Essentially, the blue line is the waveform that's created in your audio interface. It's an important nuance as true peak level matters in mastering, but digital peak matters when producing. 7 dB of overshooting is, it's the most significant overshoot possible, saying that even looking at true peak level, binary peaks lower than Gaussian. So at -12 RMS, binary's true peak is -7, whereas Gaussian's true peak is -2. So even with true peak in mind, there's a 5.5 dB difference between binary white noise and Gaussian white noise.